All right, let's go to number 4. So we have this function that's given. Actually, we have a function f of x. We don't know what f of x looks like yet, but we do have this function y that's based on f. And what y is illustrating, or what y is showing, is the value of the definite integral from 0 to x for f of t or f of x. Okay, but because I don't want to use this notation, this x and then this x again here, we will call this ft dt. All right, but x changes, of course, from 0 to 10, and of course y, which is the derivative value from 0 to x, also changes accordingly. All right, so we're asked a series of questions. When is f positive? When is f 0? When is f negative? And can you sketch the graph of f, which is not the graph of this function you are seeing? Okay, so how are they related to each other? By the fundamental theorem of calculus, which is by far the most important function, or the theorem that you are going to study in calculus, right? By the fundamental theorem of calculus, we do know that the derivative of this function, which we can call it y prime or dy dx, okay, that is the rate of change of this function, is going to be what? It is the derivative of the integral, right? And that is precisely, according to the fundamental theorem of calculus, f of x. Really? Yeah, it is. Okay, so what you're seeing is what you're seeing here is the derivative of the function that we are looking for. Okay, now we've done this before, sort of. Okay, back in chapter 4 or in earlier chapters. So when is f of x positive? Well, this happens when y prime is positive, because y prime and f of x are the same. Remember, y is not f of x here. Y is this integral function from 0 to x of the given function f of x dx. All right, but when is y prime positive? Well, that's when y is increasing. Remember, function being increasing is equivalent to the derivative of the function being positive over an interval. So when is y increasing? Well, you can tell this is my function y. It's increasing from 0 to 2. See that from here to here. Union, or keeps going down, and then from 6 to 9 seems like this is the point 9, and then after 9 it starts to decrease, right? When is f of x equal to 0? Where that's when y prime is equal to 0. That means where y is horizontal, which is where only from 4 to 6, right? And so that, and then when is f negative? That's when y prime is negative, because y prime is the same thing as f of x by the fundamental theorem of calculus. And so that happens when y is decreasing. And when is y, this graph, decreasing? The answer, 2 to maybe 4, from here all the way down here. And then stables, goes up, and then from 9 to 10. I am using the notation here, u, which is a union. That just means whether either y is between 0 and 2. I'm sorry, whether x is between 0 and 2, or between 6 and 9, and so on. Okay, so that's the answer. Those are the answers to the first 3 parts. Now, graphing f of x could be tricky, because you really can't tell precisely, what the slope is for each point of this curve. Let me go ahead and try to draw a x and y plane. I mean x and y axes. Okay, remember we are trying to graph f of x, which is actually y prime. So look at this function and try to graph the derivative, or the rate of change, or the instantaneous slope of this. So from here, 0 to 2, it seems like it's, pretty much constantly 1, right? So I think I'm just going to go somewhere close to 1. Maybe some parts are bigger than 1, some parts are lower than 1, but it's about 1. And because the slope is about the same, constantly 1 between 0 and 2, the graph of f is going to be similar to just a constant function, about 1. And then this is still, well, it looks like it is not a sharp turn or a sharp corner. So this is differentiable, which means that the derivative does exist. By the way, the derivative does exist, but it does not mean, it does not mean that the function itself, f, is continuous. You can see it's drastically going down. And by the time you get to 3, that's 0. So let me tell you what's happening here. I think what's happening here is maybe something like this. It doesn't matter which one is empty, which one is full. I think it's, oh, wait, no, it can't be that. Okay. Something like, well, it's steeper here. Maybe something like this. Okay, but the point is, it's coming down just about the slope of 1. And in fact, from 2 to 4, the slope is pretty much the same as -2, somewhere close to that, right? It's not constantly -2, but it could be something like that. All right, but the point is, all right, so here's what I need to explain. Maybe this is making things a little more difficult, okay? But bear with me, because I think it's an important point. You notice here when x is 3, y, the integral is 0, right? So that means if you add up this area and this area up to 3, between x being 0 and being 3, these two regions, the areas of the regions will cancel out, and the accumulated area between 0 and 3 is going to be 0. Okay, and that's what this point is indicating. And by the time you get to 4, of course, this number is negative, like -2 or something. And so you're going to have -2 as your cumulative, area, if you assume that the bottom part represents a negative area. But anyway, that's what's happening. Now, from 4 to 6, what do you know about 4 to 6? The function itself is going to be 0. How do you know that? Well, we just talked about that, right? Okay. And so that's what's happening. And then from 6, you're going to go up, and then looks like up to 9. What's happening between 6 and, well, let's see, from 6 to 9, the f of x is positive, right? So, well, at this point, the slope is like 2, it's even bigger than 2 first. But anyway, it goes to like something about 2 and maybe something like that. And then from 7 to 9, the increase is kind of small. So if you look at the slope of this part here, it's almost negative, or sorry, it's like 1/2, right? Constantly 1/2. So I think it'll go like this between 7 and 9. And maybe around here, it goes down to, well, it looks like the slope slowly goes from 0 to negative, like -1, like that. Okay, so it's hard to describe what this graph is doing, right? I mean, just because you are not given a nice formula. But this is the kind of thing you can do by considering like the slope at each of these points, the derivative of this red curve, which is y, at each point. Okay, 0, 0, 0, 0, 0, because here the part is the y is the tangent is horizontal and so on, right? So that's what the graph looks like. It's probably not something you could have thought of easily, right? This is a hard question, but that's what's happening. So keep this in mind. I really should add one more thing, even though it's not part of what you were asked. Remember, I just mentioned that right at this point 3, the integral becomes 0. And that's because this shaded area and this shaded area cancel each other, one on top and one on the bottom. Same thing happens at 7 and 10. Okay, so that means, you have these shaded areas and then this shaded area. If you add up the top part, that's this part and this part. Okay, with the bottom part here, they cancel out again. And then it's going to be this is going to be positive here, so that's just positive here, and then this negative part is going to cancel. And at 10, the integral of f, which is the area under the f between 0 and 10, happens to be right at 0, which means if you carefully evaluate these areas, there is the same amount of area on the top as on the bottom, canceling each other completely. And that's why this function ends at 10 right here. Okay, so that's something that you should also be aware of. That's really about, understanding calculus, not just knowing how to integrate and how to differentiate and so on. Okay, so let's pause here and then we'll go to part 3, which will start at number 5.